Welcome to Math with Professor V. In this video, we're going to do a Unit 1 review for AP Calculus AB and BC. We're going to go through most of the key topics in Unit 1, including limits, continuity, the intermediate value theorem, and trig limits. And I'm going to show you some AP style examples so you get a sense of what the exam expects. But this isn't meant to be every single detail of Unit 1. So if you need more in-depth practice or step-by-step lectures on specific topics, definitely check out the rest of my Unit 1 playlist here on my YouTube channel where I've broken everything down more thoroughly. So the goal here is to give you a solid overview, help you spot which topics you already feel comfortable with, and also highlight areas where you might want to go back and refine your understanding. If I were you, I would try to work through the examples, pause the video on your own, and then hit play and watch me solve them. Okay, first example we're going to look at is evaluating limits algebraically. Evaluate each of the following limits. And for the first few, we have little algebraic manipulations that need to be done in order for us to evaluate. First one, we've got limit as x approaches 2 of x to the fourth minus 16 over x minus 2. Always try direct substitution first, meaning try just plugging in what x is approaching, directly substituting it in and see what you get. So if I plug in 2 for x, I'd get 2 to the fourth minus 16 in the numerator. And then the denominator would give me 2 minus 2. Well, that's 0 over 0. That's an indeterminate form. So we can't determine the limit when it's in that form. Instead, what I'm going to try is factoring. I notice I have a difference of squares in the numerator. So I'm going to rewrite this. This is the limit as x approaches 2. And the numerator will factor into x squared plus 4 times x squared minus 4 over x minus 2. Now notice I haven't completely factored because x squared minus 4 is another perfect square. And make sure you still write lim in the front as x approaches 2 every step of the way until you actually are evaluating the limit. So we have x squared plus 4, x plus 2, x minus 2. X squared plus 4 doesn't factor. That's prime. It's a sum of squares. So now I can factor out x minus 2. And then we're left with the limit as x approaches 2 of x squared plus 4 times x plus 2. So now if we go ahead and try direct substitution, no problem. Don't write lim anymore. I'm going to replace x with 2. So we have 2 squared plus 4 times 2 plus 2. So this is going to be 8 times 4, which is 32. Good? Okay, so make sure your factoring is on point when attempting a lot of these problems. Next one, limit as x approaches infinity of the square root of x squared plus 18x minus x. So the problem here is that as x approaches infinity, the square root of x squared plus 18x, that's approaching infinity. And then I have minus this x over here, that's also approaching infinity. Infinity minus infinity is another indeterminate form. There's 7 indeterminate forms, just like there's 7 deadly sins. 0 over 0 is one of them. Infinity minus infinity is one. Infinity plus infinity is not. Infinity plus infinity approaches infinity. Oh, why couldn't they have made this a plus? Because they want us to do something snazzy. Okay, so what to do? Most of the time when you see an expression that involves a radical, and it's an indeterminate form, you want to multiply by the conjugate. And we're going to have to do that in the top and bottom. That way we're just multiplying by 1 and not doing anything illegal, mathematically speaking. So we have square root 18, x squared plus 18x minus x. And I'm going to multiply all of this by the conjugate, which would be square root x squared plus 18x plus x. Okay, very good. Same thing, top and bottom. And then now the beauty is you don't have to actually sit there and FOIL out the whole numerator because when you multiply out conjugate pairs, you get a difference of squares. So product of the first 2 terms, we'll get rid of the radical. So I'll have x squared plus 18x. Outer and inner products will cancel. And then I just have minus x squared left in the numerator. And then we've got all this square root x squared plus 18x plus x in the denominator. Okay, so now the x squareds cancel. And then looking at what resulted, x is going to infinity, so the numerator is approaching infinity, and the denominator, this is approaching infinity, plus this is approaching infinity, it's also approaching infinity. And you might be like, Professor V, we still have an indeterminate form. I don't think you made things better. No, but we did. So when you have infinity over infinity, okay, what we can do is divide by the highest power of x that's in the denominator. But you need to be careful because it might look like it's x squared, but see how this x squared is underneath the square root? So the square root of x squared, oh look, I got too excited. The square root of x squared simplifies to the absolute value of x, which remember is equal to x if x is greater than or equal to 0, and negative x if x is less than 0. So we have to be careful. The highest power of x isn't really x squared, it's just x to the first. I have to just decide, is it positive x to the first or negative x to the first? Well, in this case, the limit's going to positive infinity. So if we look at the piecewise function, we would be in this portion where values of x are greater than or equal to 0. So I'm just going to divide by positive x, okay? If the limit was going to negative infinity, then we would be over here, and we'd have to add like a minus sign outside of the whole expression. Okay, so in the next step, what we're going to do is divide everybody by x. Always divide by highest power from the denominator. Divide by x. All right, so now we have the limit as x approaches infinity. 18x divided by x is just 18. Now here's where you have to be careful. When I divide by x, underneath the radical, it's going to become x squared. So you have x squared over x squared plus 18x over x squared plus 1. Good. So then this is the limit as x goes to infinity, 18 over square root of 1 plus 18 over x plus 1. And then finally, as x goes to infinity, 18 over x is going to go to 0. The denominator is just 1 plus 1, which is 2. So this is 18 over 2, which is 9. And if you're like, Professor V, you did way too much too fast, this is just an overview video. I'll link all of the rest of the videos that cover the concepts that we're discussing here in more depth in the description box for you. Don't fret, I got you. Okay, next one. Limit as x approaches 0 of x squared times cosine 1 over x. So again, as x approaches 0, x squared is going to 0. 1 over x is approaching infinity. And think of cosine's graph, it has no limit as x approaches infinity, it oscillates. So this whole thing basically is like a DNE situation. But then I'm multiplying by 0. So what's going on? What's going on is it's time to use the squeeze theorem because direct substitution won't do anything for us. Okay, so here's how we're going to set her up. And a big clue that it's time to use the squeeze theorem is if you have some trig function that's easily bounded, like sine or cosine being multiplied by some algebraic expression. So we know cosine of theta is always between 1 and negative 1. So then we can say, all right, cosine of 1 over x is less than or equal to 1, greater than or equal to negative 1. Perfect. My goal is to make what's in the middle match what I'm trying to take the limit of. So look, what is this missing? It's missing an x squared. So I'm going to multiply everybody here by x squared. So then we've got negative x squared is less than or equal to x squared cosine 1 over x is less than or equal to positive x squared. And then what you do is you take the limit of the functions that act as lower and upper bounds to our function. So in this case, we're looking as the limit as x approaches 0 of negative x squared. Well, that one's easy, just direct sub, it's 0. And then similarly, do the limit of the upper bound function. Limit as x approaches 0 of positive x squared, that's also 0. So since these are equal by the squeeze theorem, what does that tell us? That forces our function to have the same limit. So the limit as x approaches 0 of x squared cosine 1 over x equals 0 also. Now, the limit of the lower bound and upper bound functions have to be the same in order for you to apply the squeeze theorem. If they don't come out the same, then that means you set something up wrong, or maybe it wasn't the time to use the squeeze theorem and you got too excited. Okay, So those are some topics to make sure you have under control when it comes to limits. Like I said, this is just a brief overview. If you need something more in-depth, check out the rest of the playlist linked in the description. Okay, next topic that's important for your AP test are one-sided and infinite limits. So one-sided limits can arise when we look at piecewise functions. Given the following piecewise function f of x, determine whether the limit as x approaches 1 of f of x exists. Now this is the two-sided limit because they didn't say from which side we're approaching 1. So it's on us to investigate the limit from the left and from the right of 1. And remember, when we're finding the limit, we're not actually interested in what the function's value is at that point. I just want to know how it behaves as we're getting near that x value. So we're going to figure out what's the limit as x approaches 1 from the left of f of x in order to answer the question. And then we'll also have to look at what's the limit as x approaches 1 from the right of f of x. So as x approaches 1 from the left, we're coming from values that are smaller than 1. So we're in this part of our piecewise function. So we're going to use x squared for f of x. And then we can just use direct substitution. You just substitute in 1. I know we're approaching 1 from the left. That doesn't mean you're going to substitute in like 0.99. Don't do anything weird like that. This is just telling you which part of the piecewise function basically we're using. So 1 squared, which is 1. Great. Now we're going to look at the limit as x approaches 1 from the right of f of x. Okay, well from the right, the piecewise function is defined to be 2x plus 1. So that's what I'm going to use for my limit. Limit as x approaches 1 from the right of 2x plus 1 is going to be 2 times 1 plus 1, which is 3. Now these are not equal. So you should say since the limit as x approaches 1 from the left of f of x equals 1, which does not equal the limit as x approaches 1 from the right of f of x, which equals 3, then we say the limit as x approaches 1 of f of x, it doesn't equal anything. It just does not exist. Okay? Very good. Now, another scenario where you would have to deal with the piecewise function, it's kind of a sneaky one, it's in disguise, is if you're given an absolute value function. So here we're looking at the limit as x approaches -5 from the left of x plus 3 times absolute value of x plus 5 over x plus 5. So the key is to start off rewriting absolute value x plus 5 as a piecewise function. I have a whole video on how to do that. But basically you're going to split the domain wherever the expression inside the absolute value bars is equal to 0. So just set it equal to 0 in your head. You'd get x is -5. So split the domain there. Part of the piecewise functions for x greater than or equal to -5, and then part of it is for x less than -5. If you're plugging in values bigger than -5, everything inside is already positive, so absolute value does nothing. So it just gives you back x plus 5, and then it'll give you back the opposite value on the other side. I'm explaining this quickly, like I said. If you need more, go watch it. So then what does this mean for us? Well, watch. So we have the limit as x approaches -5 from the left, x plus 3. And then instead of absolute value of x plus 5, I'm going to look at my piecewise function. Since we're coming from the left, we're in this part of the piecewise function. So I'm going to replace absolute value of x plus 5 with -x plus 5. And then over x plus 5 like that. This cancels. And then now we should be in a good place just to use direct substitution, right? So x goes to -5 from the left. I'm going to write this minus sign in the front. It looks kind of weird over there. -x plus 3. And then just plug in -5 for x. So -5 plus 3, that's -2 times another negative is +2. What an ugly 2. Oh no, you can't stay. Okay, that's much better. All right, good. Let's look at a pretty tricky limit to wrap up this idea. We have the limit as x approaches -1 from the left of x squared minus 5x plus 4 over x cubed minus x. So that first limit we looked at, just try direct substitution first, plugging in -1 in the numerator. So we'd get -1 squared minus 5 times -1 plus 4. And then in the denominator, Negative 1 cubed, that's going to be negative 1 minus negative 1. Okay, so already I can tell the denominator is going to be 0. In the numerator, what is that? Positive 1 plus 5 plus 4. That's 10. So we have 10 over 0. When you have a non-zero constant over 0, that means the entire expression is getting larger and larger and larger, because think, you're dividing by something that's getting tinier, tinier, tinier. The only thing is we need to figure out, is it getting large in the positive or the negative direction? So there's a couple different ways to do this depending on what your teacher taught you. You can make a sign chart, or you can just plug in values that are a wee bit, in this case, smaller than negative 1 because we're coming from the left. I'll show you a few variations. I'm noticing, though, that everything in the numerator and denominator factors, and so I'm tempted to just go for it and cancel just to clean things up and make our life easier. So it'll factor, right? X minus 4, X minus 1. Oh, yeah. And then in the denominator, I could take out an X, and it's X squared minus 1, which also factors further. So let's just factor our little hearts out. And then X minus 1 is going to cancel. So we've got limit X approaches negative 1 from the left, X minus 4 over X plus 1. So what you could do, if your teacher taught you the whole little sign chart situation, you want to list all the zeros from the numerator and denominator on there. So we've got negative 1, 0. Note, it's not to scale. It's fine. Nobody cares. And in this case, we're approaching negative 1 from the left, from this side. So pick a number over here, say X equals negative 2, just to see what the sign of the expression is, okay? So if I substitute in negative 2 in the numerator, negative 2 minus 4, that's negative 6. This is going to be negative, who cares what it is, it's negative. And then negative 2 plus 1, that's also negative. So we've got a negative in the numerator, a negative and a negative, so this whole expression is negative. So when I'm approaching negative 1 from the left, this expression's getting bigger, 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 but in the negative direction. So that tells me this limit's going to be negative infinity. Okay, I didn't really use a sign chart. The only thing that you want to be careful, like I was allowed to pick negative 2 because there were no zeros of this expression on the other side of negative 1. So that's why you always want to list out the zeros from the expression. If negative 2 was a 0, I would have had to pick something between negative 2 and negative 1. Okay, if your teacher taught you a different way and it's working for you, do it. Don't stress. Just showing you some options. Okay, next, continuity. So find the values of A and B so that f is continuous at every point. So looking here, we've got this cute little piecewise function. And notice this top function, it's a rational function. Rational functions are continuous on their domain. We have a theorem that tells us that, so we don't have to go proving that it's continuous. And then here, another little polynomial, quadratic polynomial, linear polynomial. All of those are continuous on their domains. So the only issue is coming from the fact that this is a piecewise function, and I don't know if when the domain splits or when I'm pasting these pieces of the functions together, I'm doing so in a way where one picks up right where the other one leaves off, right where the other one leaves off. You don't know. Or are they doing something wild like this? Who knows? So how do you check? Well, you check the limit from the left and from the right every time the piecewise function is pasted to another function. So we've got a couple spots to check. We have to check where x is equal to 2, and then we have to check where x is equal to 3. But we can do it. We got this. We're professionals. So let's just write ourselves a little note. We're good to go everywhere except at x equals 2 and x equals 3. Okay, perfect. So let's look at what's the limit as x approaches 2 from the left. Well, we're going to be in this part of the piecewise function, right? So that's x squared minus 4 over x minus 2. Can you use direct substitution for this limit? No, you'd get 0 over 0. Womp womp. So what do? No, you don't sit there and cry. You factor. Okay, so x approaches 2 from the left. x plus 2, x minus 2 over x minus 2. Perfect. Cancel, cancel. Now can we use direct substitution? You bet. So 2 plus 2 is 4. They're like, what did you do in math today? We did 2 plus 2 is 4 in my calculus class. Okay. Now let's check from the other side. What's the limit as x approaches 2 from the right of ax squared minus bx plus 3? Well, I can substitute in 2 for x. The rest I'm just going to have to leave in there. So a times 2 squared minus b times 2 plus 3. That's going to be 4a minus 2b plus 3. Okay. In order for this function to be continuous, the limit as x approaches 2 from the left has to equal the limit as x approaches 2 from the right. So what do I know? This tells me 4a minus 2b plus 3, it better equal 4. Oh yeah, so 4a minus 2b had better equal 1. I'm going to leave that there, save it. I have 2 unknowns and only 1 equation. I can go nowhere with that. So that's why we have to check what's going on with 3. And I have a feeling we're going to have another equation with the same 2 variables and then we'll be in business. Okay, so now let's check the limit as x approaches 3 from the left of ax squared minus bx plus 3. So we're going to have a times 3 squared minus b times 3 plus 3. So that's 9a minus 3b plus 3. Okay, cute, cute. Then we have to check from the right. From the right means from values larger than 3. So which part of the piecewise function would we be in? This one right here, yes? 2x minus a plus b. 2x minus a plus b. So this would be 6 minus a plus b. Okay, for the function to be continuous at x equals 3, it has to be defined there, and then the limit from the left has to equal the limit from the right. So we need 9a minus 3b plus 3 to equal 6 minus a plus b. Let me put it in standard form like the other one. So we would have 10a minus 4b equals 3. Yay, okay, perfect. Now let's see. I think easiest thing to do to solve this system of equations is elimination. Let me multiply this equation up here by -2. So then it would be -8a plus 4b equals -2. Add them together, that's 2a equals 1. So a is a half. And then if a is 1/2, I'll let you verify b should also be 1/2. Okay, very good. Now remember there's 3 conditions for continuity. One is that f of a exists, continuity at x equals a. Second is that the limit as x approaches a of f of x exists as a finite number. And this implies that the limit from the left equals the limit from the right. This is what we've been stressing about in this problem. And then the third thing is you just got to make sure the function value from part 1 equals what the limit is. As long as the limit exists, though, you're good to go. You can define the function however you need with the piecewise function or whatever. So if it passes condition 2, then we say if there's any discontinuities, it's removable. Discontinuity. Okay, there's a whole discussion we can have about that. It's very important. So make sure you check out the in-depth video lecture should you need it. Okay, are we good? Moving on. Use the graph to find all points where the function is discontinuous and identify which conditions of continuity fail. Ooh, okay, here we go. So right off the bat, x equals -4, x equals -1, and x equals 2. Let's investigate what's going on at each of these. So at x equals -4, first, is f of -4 defined? Do you see a function value, a point on the graph, a y value where x is -4? No, I see this side's approaching positive infinity, this side's approaching negative infinity, but I don't see an actual function value when x is -4, so no. F of -4 is not defined. So already it fails condition 1. Condition 2 also fails. The limit as x approaches -4 of f of x does not exist, because we just said the limit from the left doesn't equal the limit from the right. And also for condition 2 to pass, the limit has to be a finite number. So even if they were both going to positive infinity or negative infinity, not good enough. It has to be a finite number. 4 from the left, -4 from the left is going to negative infinity. And then -4 from the right is positive infinity, right? Yeah. Okay, let's be thorough. All right, that's how that one's failing. Okay, what about at x equals -1? Okay, condition 1, is f of -1 defined? Yeah, there's a function value when x is -1, so that's not the problem. Does the limit exist? Yeah, it does. This is funky. The limit as x approaches -1 from the left equals the same thing as from the right, so the limit exists. The problem is that the function value does not equal the limit. So let's be specific. It only fails condition 3. Okay, so the limit as x approaches -1 of f of x, that limit, I mean, it looks like it's a half, right? And that doesn't equal f of -1, which looks like it's 2. Okay, so this kind of discontinuity, if they were to ask you, this one's removable because condition 2 is not violated. This one is, the first one earlier, not removable because condition 2 failed. Okay, last one we're going to investigate. Let me just do the work over here so you can see. Is that x equals +2. So it fails in a couple places. 1, f of 2 is undefined. And then does the limit as x approach 2 exist? No, right? The limit as x approaches 2 from the left of f of x, it looks like it's 3.5. And that does not equal the limit as x approaches 2 from the right of f of x. That looks like it's 1. So then we would say the limit as x approaches 2 of f of x does not exist. So since it failed condition 2, this one's not removable. As long as the limit exists as a finite number, the discontinuity is removable. You got it? Oh, good. Okay. Okay, next problem deals with the intermediate value theorem. So the question states, use the intermediate value theorem to prove that 7 sine x equals x has a solution between pi/2 and pi. So to apply the intermediate value theorem, I need a function. So let's make one. So I'm going to let f of x equal 7 sine x minus x, and I want to show that f of x attains the value 0 on the interval from pi/2 to pi. That is, I want to show that there exists, do you know the shortcut or math symbol for writing there exists? It's like a backwards E. There exists some number C that's on the interval from pi/2 to pi. It has to be the open interval, such that ST, that's not a fake abbreviation. The first time my calc teacher wrote that on the board, I was like, why is this man so lazy abbreviating such that? But it's legit. Such that f of c equals 0. If I can show that there exists some value c on this interval where my function would be 0, then that's equivalent to showing that the equation has a solution between pi/2 and pi. I don't have to actually find it. I don't have to find c. Cool, right? So in order to apply the intermediate value theorem, first we have to verify that this function is continuous on the interval, in this case pi/2 to pi. Well, you don't have to use your 3-part definition of continuity. No. All you need to do is use a theorem that tells you this function is continuous on its domain and identify what kind of function we're dealing with. So f of x is a combination of a trig function, right, 7 sine x, and polynomial. So the theorem applies, so it is continuous on its domain. So we have to identify what its domain is. What is its domain? That's right, all real numbers. So therefore, if it's continuous on all real numbers, it's continuous on pi over 2 to pi. So we can use the intermediate value theorem. Hooray! If it wasn't continuous, can't use it. Okay, now what we do is we substitute in or plug in pi over 2 and pi into the function. So f of pi over 2 would be 7 sine pi over 2 minus pi over 2, which is 7 minus pi over 2, which is going to give us, who cares, but it's positive. And then f of pi would be 7 sine pi minus pi. 7 times sine of pi, that's 0, minus pi, that's negative pi, which is negative. So since I showed that the function value on one side of the interval is negative and then the other side it's positive, what does that tell me? This implies that there exists some number c that's on the interval, open interval, from pi over 2 to pi. I know c isn't one of the endpoints because we plugged in the endpoints. One was negative, one was positive, such that f of c equals 0. And then this means the equation has a solution in the interval pi over 2 to pi. So if you draw like just the roughest of sketches to give yourself an idea of what's going on, if you understand it, this theorem shouldn't be so daunting. Pi over 2, pi. We plugged it in to f of x. At pi over 2, it was positive. At pi, it was negative. Since it's continuous, I know nothing wild like this is occurring. No. That means what had to happen was somewhere it crossed the x-axis. That somewhere is c. F of c is 0. I don't know where c is. I don't need to find it. I just know that this happened, and that's good enough. That's what they're asking me to do in this problem. Cool? Okay, perfect. Last idea deals with trig limits. I have a whole video on this, so if it's something you struggle with, check out that video. I'm going to do 2 examples, but I got plenty more in that video to make you a professional by the end of it. Yep. Okay, so we've got the limit as x approaches 0, sine x cosine 4x over x plus x cosine 5x. You got to remember 2 things. 2 things. The limit as theta approaches 0 of sine theta over theta equals, that's it, 1. You could also flip this around. Limit as theta approaches 0 of theta, that's a theta, over sine theta would also be 1. Because reciprocal of 1 is 1. So you can give this little flipperoo, same thing. Other limit that you need to remember, as theta approaches 0 of 1 minus cosine theta over theta, that's also 0. Can you flip it around? No, because 1 over 0 does not approach 0. But you could switch the order of subtraction. Does that excite you a little bit? Cosine theta minus 1. That would change the sign, but negative 0 is still the same as 0. So that's all we can do with that guy. Okay, these are like your lifelines when doing these trig limits, okay? They'll pop up. So I'm looking, see how we can factor an x out from the bottom? Let's try that. So, also, of course, we tried direct substitution and we got 0 over 0 first. Okay, limit as x approaches 0, we have sine x cosine 4x over, take out the x, now it's 1 plus cosine 5x. And then let's rewrite this. Limit x goes to 0, put sine x over x together, and then leave the rest over here. Cosine 4x over 1 plus cosine 5x. Now look what happens. As x goes to 0, sine x over x, that goes to 1, based on this. And then cosine of 4 times 0, that goes to 1, that goes to 1. So now I have 1 times 1 over 1 plus 1, that's 2. So the limit is a half. Bravo. Did you get it? Are you working these out on your own? I hope you are. Okay, next one. Limit as x approaches 0 of cosine x minus 1 over 2x squared. So you're probably like, ooh, this reminds me of this guy, right? But we have a problem. So say you write it as cosine x minus 1, you take one of the x's out, then you would still have 1 over 2x, right? Maybe you were thinking that? Okay. This is going to 0, and then this is where things are funky. This is going to 0. 1 over 0, that approaches infinity, positive infinity or negative infinity. And so this is problematic because 0 times infinity, that's also an indeterminate form. Oh no. Oh no. So that was not the move, unfortunately. So what do? We don't sit and cry. We go, oh, cosine x minus 1, another trick I have up my sleeve. Let me multiply by the conjugate, namely cosine x plus 1, and then see if we can get some Pythagorean identities up in here that might help us. Cosine x plus 1. So we've got limit, x goes to 0. This is going to be cosine squared x minus 1 over 2x squared times cosine x plus 1. Now be careful. Sine squared x plus cosine squared x is 1. Cosine squared x minus 1 is negative sine squared x, right? Because the sign's reversed. So replace the numerator with negative sine squared x. So we've got limit, x goes to 0, negative sine squared x over 2x squared times cosine x plus 1. Now, we've kind of flipped the script. We're going to actually use this limit property. Since I have sine squared and x squared, you can break it down. You have a few options. Let me do it like the easy way. Take the constants kind of out front so they don't bother you. So let's write this negative 1/2. I have sine squared x. So that's sine x times another sine x. I've got x squared. Each of them get their own x. Look at that. So equitable. Over 1 times 1 over cosine x plus 1. Are we happy? Can we evaluate this limit? Okay, this is a constant. This goes to 1. This goes to 1. Cosine of 0, 1. That goes to 1/2. So altogether, this is going to be negative 1/4. Voila. That's a fun one, right? Definitely tricky. Definitely tricky. You might be like, Professor V, I would have never thought to multiply by the conjugate. Well, you know, sometimes you just have a list of little maneuvers or options in your head and you just got to run through them. And when you've done enough problems, those little tips and tricks will pop in your head faster, okay? I've got a lot of years on you guys. Don't feel badly. So that's it for this AP Calculus Unit 1 review video. I hope working through these examples gave you a good sense of the key ideas in limits and continuity and also helped you see which areas you might need to review a little bit more in depth. So if you want to go deeper, definitely check out my Unit 1 playlist for more comprehensive lessons. And if you'd like some extra practice, I might post guided notes and worksheets over on my Patreon. So grab those if you want some structured review. Make sure you give this video a thumbs up, subscribe if you haven't already, share it with your classmates, friends, whoever you think might enjoy it, and follow me on Instagram and TikTok, Math with Professor V, for more math content. I'll be back sooner than later with the Unit 2 review. Thanks so much for watching.